In the last video, we were talking about hyperbolic trigonometric functions, and we said, okay, if we have this hyperbola here, you can call it a unit hyperbola if you want, but if we were to parameterize this unit hyperbola, we could let x be equal to cosh of t and y be equal to sinh of t, and as t varies, it's going to draw out this right branch of this hyperbola. So that is kind of how we think about the hyperbolic trig functions there. And I have given you the definitions of both sinh and cosh in terms of e of x, e to the x. And what we have here are the graphs of sinh and cosh on their own. So the question is, all right, we're talking about these, but we're in a calculus class, so we want to talk about their derivatives. We want to figure out what the derivatives of these are. And more importantly, are these analogous? Are these analogous to our circular trig functions and their derivatives? So we're going to find that out in this video. So again, if you know the chain rule, please feel free to pause the video and try to find the derivatives of both sinh and cosh. All right, assuming that you've given it a go, let's begin. So let's first take the derivative of sinh and see what we get. So the derivative of sinh of x is equal to derivative of e to the x is e to the x minus, and we're going to use some chain rule, e to the negative x times the derivative of negative x, just the chain rule, which is -1. And then we have that all over 2. So then cleaning this up, we have e to the x, and then we have plus e to the negative x, and all of this is still over 2. And what is this here? Well, you can look up and you could see this is cosh. This is cosh of x. So the derivative of sinh is cosh of x. So that's pretty cool because remember, circular trig functions, derivative of sine of x is cosine of x. So we see an analogy there. So now let's figure out what the derivative of cosh is. All right, let's find cosh. Derivative of cosh is equal to, well, we have e to the x plus, again, we're going to use the chain rule, e to the negative x times -1. And all of this is over 2. All of this is over 2. And then we have e to the x minus e to the negative x, all over 2. And what is this here? Well, it's sinh of x. So the derivative of cosh is sinh, and that might be a little different than what you thought because, again, the derivative of cosine, circular cosine, is negative sine. So a little different here. We have cosh, the derivative of cosh being positive sinh. So that's what we have here. And again, let's just confirm this graphically. We want to make sure we did some good work over here in calculating the derivatives. So we have the graphs over here. Let's first look at sinh, the graph of sinh, and we're claiming that its derivative is cosh. So let's make sense of that graphically. So as we move along sinh, we have, looking at the slopes here, we have a positive slope. So our derivative graph should also be positive, which it is. And then as we move along, this slope here, our positive slope, is becoming less and less positive. It's still positive, but it's decreasing. So we see that our derivative graph is mirroring the same. And then after this slope decreases, it then starts increasing again. And that's exactly what this derivative graph does as well. It starts to become more and more positive. So that's fitting well with what we thought. And now let's look at cosh, and we're claiming that sinh is its derivative. So as we move along cosh, again, we're looking at the slope here. The slope here is negative, and our derivative graph is also negative, so that's fitting. And then as we keep moving along, our slopes here are becoming closer and closer to 0. So they're increasing, but they're getting closer and closer to 0 into this minimum point, and our derivative graph is also going through 0. So that is matching up, and then as we leave this minimum point, the slope is becoming more and more positive. So our derivative graph should also be positive, and it is. So both graphically and how we calculated this using the chain rule, we can feel good about our derivatives. And maybe you've been asking, maybe you've been wondering, okay, we have sinh and cosh. Can we talk about the hyperbolic tangent function? Well, sure, we can talk about the hyperbolic tangent function. Let's do that. Hyperbolic tangent function. And we're going to define the hyperbolic tangent function as sinh of x over cosh of x. And then similar to how we take the derivative of the circular tangent function, we're going to use the quotient rule. So let's use the quotient rule here. We have the hyperbolic tangent function, and we're taking its derivative by the quotient rule. So the derivative of the top here, derivative of sinh, we found to be cosh. And then we are multiplying by the bottom by cosh of x, and then minus. Now we keep the top. So sinh of x times the derivative of the bottom, which we found to be sinh. Derivative of cosh is sinh of x. And then all of this is over our bottom squared. So cosh squared, all over cosh squared. So now our numerator reduces to something pretty cool. This is cosh squared minus sinh squared. And if we look at how we parameterized this hyperbola, and under these parameters here, we have cosh squared minus sinh squared, and that is equal to 1. And that's exactly what we have in this numerator here. So our numerator reduces to 1, and that is a hyperbolic trigonometric identity. So we have 1 over, still we have cosh squared in the denominator, and we can call this the hyperbolic secant function squared. And you can see, again, another analogy here, because the derivative of our circular tangent function is secant squared, and our hyperbolic tangent function, its derivative, is also the hyperbolic secant function squared. So again, you can see a lot of analogies going on here with the hyperbolic and circular trig functions and their derivatives, which is pretty cool. And again, why are we talking about this? Well, these derivatives here are going to be some tools that we can use later on, especially when we talk about integration and trigonometric substitutions. So they're important to talk about, and also just to show you some analogies between circular and hyperbolic trig functions. And real quick, before we go, if you ever forget these definitions up here, like if we have does sinh get a negative or a positive sign? I can't remember. Well, you can just go back, and this is kind of how I remember them. You can just go back to this hyperbola and how we parameterized it and recognize, okay, well, cosh can only be positive on this right branch, and sinh can be negative, both positive and negative. So that helps me to remember that sinh gets a negative sign and cosh gets a positive sign. And once you have these, again, you can derive their derivatives just through the chain rule.